Hello, hello. The board is hello. More people. Hello. Hello, hello, hello. I'm just getting the board going. Good to see you. I will say specific hellos in 1 second. I don't know why the board. Give me 1 second. Excuse me. Okay, we should hello, Lucas. Oh, hello. Well, okay, wait. Hello, Melita. Hello, Cheska. Hello, Michelle. Hello, Amanda. Hello, Michelle Q. That first Michelle was a Michelle F. Uh, hello, Amanda. Bless you. Oh, did I sneeze? Thank you. I was going to say, wow, I get a blessing before I even do anything. That's great. All right. Good afternoon. Hi, you. I must have sneezed. Good afternoon, Melita. Good afternoon, Matthew. Good afternoon, Freddie. Hello, Michelle Q. Good afternoon, Marilyn. Okay. On board. Wait, board coming. Hold on. Okay. Okay. Very quickly, I will say, it was thank you very much for doing the course evaluations last time. And again, it's like all awkward. I don't know who did what or what. I don't see the individual ones, and I shouldn't, and I don't, and I can't if I, etc. But I did that. Okay, great. Someone just said something in the direct. Oh, okay, great. There's one person in the direct chat. Oh, okay. Okay. So, all right, that will skip that in. So I will just say, yeah, I did this unusual thing this semester of putting the link in a assignment portal, which was a questionable thing to do. It was just to make the link accessible to you. But I certainly can't. It's not an assignment that you do the course evaluations. I mean, I can't require that, and I can't give you points for that, or I certainly can't give you points for content. Maybe I can give you all points for having done them. See, I don't even think I can do that because I think that's weird. So, but I did notice that many of you, I didn't realize. So I did notice that many people did them. Like again, I didn't realize that by putting the link in the assignment portal, then suddenly I would get a sense of the numbers of who did them. And that's all I know is the numbers of like how many people did them. So thank you very much. That's all I know, and that's all I should know. I keep saying that because I've never put it in the assignment portal before. Maybe that was good, but I'm here to say, and I know some people had trouble with the link, but then other people helped them. So that's all great. I will say though, because they are that important, I will again, if anybody reminds me, I will end class today like 10 minutes early. I mean, most of you have done them, but some people haven't had a chance. If you remind me like 15 minutes before the end of the period, I will end class, or I will stop talking at like 10 minutes before the end, but I'll keep the Zoom thing open. I'll stay here so that anybody who can still do them before you go to your next class, or like you could do it on my, you get what I'm saying. I'll end class 10 minutes early for anybody who needs more time to do the evaluations. And obviously, if you've already done them, then just take off. But again, even though I find they are really important. They're more important than you know. And they're so important that they make me nervous every time I talk about them. So enough of that. But it is true. And then once it's all over, I could tell you more, or next semester, I could talk to you more details about what, give us 50. Okay, I will. Okay, I will give you 50. I see. I can. That's where it gets awkward because I can't get into that. I mean, but yes, I will give you 50. If 15 helps, I'll give you 15. But oh my god. Okay. On a joke, I'll now. Okay. Well. Okay. But yeah, I can't even make jokes about them because they're. I mean, I can't help it. But it's all yeah. But I will. So I'm going to shift gears and make this joke. Wait, can I make this joke? Wait. I mean, there was a, yes, I can. All right. Oh, wait. Well, okay, wait. All right. So quickly on so first of all, I will make the joke, Amanda. Thank you. Okay, I will. But also on what Christopher says, I mean, what Chris says, which is funny, but it's not funny. Like he wrote it would be funny if teachers review us. Like that is funny, except that, of course, I mean, arguably that's what a grade is. Well, I mean, let me put it a different way. yes, it would be funny if we reviewed you. I mean, that would be hilarious. But I think the real issue, one of the main reasons that we do the course evaluations is we already have a sort of disproportionate power over your life because of like the reality of reality. But we already do, because we give you grades and all that. And all that makes me very uncomfortable, as I think you can tell. So the evaluations are like the one place where the power goes back for like a moment. Now, sadly, most students don't actually believe that the instrument is as powerful as it is. And I'm happy when the course is over, or at least the period evaluation is over, I can talk to you all more about the details of exactly what happened with these evaluations, because I do know, because I have been on the college committee that administers or whatever that's behind them. I've been on that committee for years. So I actually do know something about like what goes on behind, and I can guarantee you that we never, ever, ever, we go through a lot of pains to make sure that no teacher ever knows the individual like student behind any individual eval. And we never really look at individual evals, but the aggregate results of them, they go into personnel files in a way that is so important that it actually is very controversial among professors. Just so you know, like that you actually do to have the ability to get your voice across through these things, like more than you might believe. Okay, but I just keep saying that. I can be more detailed like when it's all over. Okay, but oh my God, whoa, Jessica, throwing down that's a throw down. Wow, worth my. You're gonna shoot. You're like, whoa. Wait, does that mean she's gonna? All right, well, if you mean during like the 15 minutes that I'm letting it. Okay, wait, but don't do it yet. Wait, I promise. Wait, okay, hold on. You guys are driving me crazy. We still have that end the semester with some material. No, if Jessica wants to do that, like in the last, well, I don't know how we're gonna. Just remind me when there's 15 minutes left of the period, and we'll see what happens. But I'm not. I mean, she certainly has my attention now. The last thing on the Amanda joke. I mean, on the joke that Amanda's making me. Just so you know, like another thing that's like shady, but not nearly as shady as this is you. Years ago, or like somewhere toward the beginning of COVID, when I started doing the videos of the Zoom classes and blah 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 blah, someone, okay, I'm just admitting this, and now I'm going to say this on the recording. It is the case that years ago, someone like took a quick clip of me or whatever and turned it into like a TikTok or something. I think it was a TikTok, and wrote at the bottom something like, if you give this crazy ADHD professor, and I'm just telling you what they said. If you give this ADHD professor 100 subscribers on his YouTube channel, he'll give us all A's, which I never said. I could never say a thing like that for 1,000 reasons, obviously. But she did write that, and she made a TikTok out of it. And like it went momentarily a little, not viral, but it went a little bit bananas momentarily. And that's like the reason that I have like if you've ever looked at, and the numbers spiked on YouTube because of that. But of course, then I had to make a million recordings, like taking it all back, because I can't make that deal, and I wouldn't, and blah blah blah. But and I mean, I don't, and also that possibly is an offensive use of. I mean, anyway, I mean, for anybody who, okay, I'm gonna stop. But that's what. Okay, that is what. Oh, you know it. Oh, the video is 14 seconds long. Okay. Okay, yeah, all right. See, and now anybody who actually has been clinically diagnosed is probably offended to be in the same camp as me. So I just got to walk away from this now. But all right, if it's 14 seconds at the end, we will. All right, fine. It's 14 seconds. Go for it right now, Jessica. Go for it. If it's as long as we're in this space, just go for it. Okay, and Felix 100 subs and Felix teaches. That's hilarious. Okay, it is funny. I guess that's why I'm telling you. But I hope it's not. If it's offensive to anybody in the room, please let me know privately, and I'll try to make it up to you. But okay, Cheska, do you need permission to share screen? Go for it. I can't believe I'm letting this happen. Wait, who can start? Okay. I think I just gave you permission. I mean, I think I could just give. Okay, here she goes. Oh my God, I'm scared. What the? Oh my God. Wait, but why is there no sound? But okay. Oh my God. Okay, that is All right, that was worth it, I think. Might have been even more worth it with the sound, but yes, that is awesome. And I do love Squirtle. And yes, I mean, after grass starters, water starters are awesome. No, that's okay. Wait, is she okay? That was awesome. Yay, thank you. I mean, wait, Squirtle, he evolves into War Turtle, right? But is there a middle evolution? I forget. Yeah, of course there. Oh, yeah, War Turtle, and then there's totally. Wait, yeah, it's sad. Oh, but you could hear. Well, I couldn't hear it, but maybe that's. Wait, am I been on mute this whole time? Yeah, I couldn't hear it, but all right, yeah, we'll check it out. But that's awesome. Wait, it goes Squirtle, War Turtle, and then Empoleon, right? Or am I confusing? Is Empoleon the evolution of? Empoleon is a beast, or oh, Blastoise, right, Blastoise, of course, right, with the two, yeah, who just, all right, that's actually right there, okay. Oh, Empoleon comes, oh, nice, oh, you guys, now I know who the real physicist in the room, no, just totally kidding, but yes, Empoleon is Piplup, right, and Piplup is my wife's favorite evolution. She doesn't like Pokemon at all, but that's the one that she thinks is the cutest. Okay, Gen 4 water, so lit, you guys, all right, we got to do physics now, but yes, the turtle is called, yes. And seeing Chris has the courage and honesty to admit his Pokemon deficiency. Yes. All right, we've got to do physics. This is ridiculous, especially for the dude, even though whoa. And you just got roasted by Michelle F. That takes something also. Don't think I'm not noticing that. I'm not saying Michelle. I mean, Michelle F, she doesn't just roast randomly. That must have been all right. Anyway, all right.
Yes, I do. Yes, I do.
Wow. Oh my God. All right. By the way, you could submit all that for voice. You just use voice, but at least in the physics. All right. I take it all back. I'm roasting myself. I'm in deep trouble now. All right. Only me. All right. We're going to do physics. I can't believe this. Although the dude, even I know that. That is wow. Okay. All right. Well, I hope I didn't just accidentally roast Michelle F by saying that she doesn't know. God forbid. I mean, Quark forbid. Like roast away, set the oven to 400 degrees in preheat. What can I mean, just, yeah. All right. But why, where's the no share screen? Oh, because, yeah. All right, this is ridiculous. It's amazing anybody learns anything. Actually, do we know for a fact? We don't know if anybody learns anything. Okay. No, you do. All right, I'm going to share the screen. We're going to do this by Cracky. Okay, here we go. Actually, and you know what I'm going to do? You know what I'm going to do now to make up a little time here? I am going to I'm going to skip a couple pages in the PDF. Like you'll get it uploaded anyway. What am I going to do? Amanda, oh my God. I am going to miss this class after it kills me. So what we're dealing right now is with work and transfer of energy. I'm going to in like 2 sentences, summarize the next couple of pages and get straight to what I think most people want, which is, I'm going to try to move quickly to starting to go over the homework that's on this. Again, you can still do it. If you haven't done it yet, blah, 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 I'm still, but either way, we're going to get to it in a minute. Let me just say, notice summary. Yeah. The integral at the top, right? Or this business that's here. Remember, this is a summary of what we did last week. This is the definition of work. Something that this class sometimes doesn't know. Oh, no, this is the definition of work, right? This is the triple equal sign. This is what work means. What it means is the path integral of force, which in English means like the product of how hard you push or pull something with the full displacement that you push or pull it, right? Work is interaction times result. It's force times displacement, right? But in this complicated calculus dot product-y way, because of all the details that we discussed last week, like that you have to take into account the angle, that you have to add up all the little infinitesimal sections of the displacement, all that stuff. But in the end of the day, in simplest possible terms, 1 joule of work is defined to be 1 Newton of force times 1 meter of displacement, right? That's what work is. But the reason we care, right? So that's a summary of last week. The reason we care is because of what it does. Double equal sign now, right? What it does when you have a bunch of forces acting on an object, so that at the end of the day, you have a net force acting on an object, then you can add up the work being done by all of those different forces and compute or identify what you would call the net work being done on that object. And the result of doing net work on an object is that you change the object's 1 FMV squared, right? In fact, you end up, if you do positive work on an object, you give to the object 1 FMV squared, right? Now I'm saying 1 FMV squared like that, like in a weird way, because at first this is just purely an algebraic result. Like I want to emphasize, we're not assuming that you already have some idea of 1 FMV squared before you go into this. Like you might have heard it in high school or some other class, but we're not referring to that. This is like the invention or the discovery of it here, is we're saying when you push or pull something through a distance, what if you push or pull something to the north and in fact you succeed in displacing it to the north, then you raise the value of a certain measurement of that object. Now you don't, but it's complicated. If you do 3 joules of positive work on an object, what it would be nice and simple if it was like, oh, by doing 3 joules of work on an object, you raise the speed of the object by 3 units. Like that would be nice, but it's not the case. Life is not that simple. And frankly, life couldn't be that simple because speed is measured in meters per second and work is measured in joules. So it's not that simple. But what is the case is if you have some object and you measure its mass, and you take half of that, and you measure its speed, and you square that, and you put these things together, the half mass times the square of the speed, if you work out the units of that, you will find that the units of that are, in fact, joules. I'm not going to spend the time now, but that would be a good homework exercise. You can show yourself that kilograms times meters per second squared are, in fact, the same thing as newtons times meters. In fact, even when I say it that way, I bet there are some people in the room that can even see that in their minds, right? Like kilograms times like mass times square of speed. Mass is in kilograms. Square of speed is in meters squared per second squared. So 1/2 mv squared is kilograms times meter squared per second squared, which is the same thing as kilograms times meter per second squared times meters. So, and a unit of force is a kilogram times a meter per second squared, like F net equals MA. Like I'm speaking fast, you're getting to whatever level you're getting it, but I'm just saying, it turns out that if you look at an object and you measure its mass and you measure its speed and you square the speed and you divide the mass by 2 and you put those 2 things together, you multiply those 2 things together, you get a number in joules. If you now do 7 joules of positive work on that object's half mass square speed will go up by precisely 7 joules. Right? So this quantity, this package of measurements, half the mass times square of the speed, is really worth tracking because it is the package of measurements that changes according to or as a result of net work being done on objects. So just because the algebra spits that out, just because the algebra, like I would never have predicted that. I'm not here saying like, isn't that obviously logical that if you did work on something, you increase its half mass square speed by the exact. I'm saying it is logical, but I'm not saying like I would have seen that coming. It's just what the algebra shows. So therefore, from now on, we give a name to that package. We could call it half mass square speed, but that's like, first of all, that already basically sounds like it sounds like SpongeBob SquarePants, and it's too awkward. So we give it a name called kinetic energy. And we say from now on that when you do positive work on an object, when one object does positive work on another object, the first object raises the second object's kinetic energy by exactly the number of joules of the work done, right? And when it does that, if I do positive work of 5 joules on you, I will give you 5 joules of what we're now calling kinetic energy. Where do you get your kinetic energy will go up by 5. Where does that come from? comes from the work that I did on you. So my kinetic energy will go down by 5. Like that's sort of a duh, but it's sort of not. So at the end of the day, what I'm saying is when you do work, what you do is you transfer kinetic energy from the thing doing the work to the thing being worked on. And if you were to do negative work, it's the same thing in reverse. If I do negative 5 joules of work on you, then I gain 5 joules of kinetic energy at the expense of you. So this is why I use the word transfer from now on. Work is the transfer of energy. Work is the transaction. Energy is the commodity, so to speak, right? So I'm just summarizing what these pages say. Okay, this page is what I just said. If one mass does positive net work, again, obviously, of course, I'm going to upload this PDF. So, but if one mass does positive net work on a second mass, then the second mass gains an amount of kinetic energy precisely equal to the net work done, and the first mass loses the K. That's just what I just said. Okay, all together saying it's a transfer. Okay. Oh, so we're going to get to the homework now. But one thing I didn't put in notes, you really, all joking aside, you really might want to write this down. Like, now again, remember, you've got to keep, all of us have to keep straight the difference between triple equal signs and double equal signs. What work is the path integral of force, the continuous sum of force times displacement, taking into account directions. Right, that's what work is. What work does, so that's a triple equal sign. What work does, what it accomplishes, why we care about it, is that it transfers kinetic energy. Mathematically, kinetic energy is 1/2 mv squared. But you might very well ask in English, what is kinetic energy? Like, what is it? Like, so what if I give you more kinetic energy, what have I given you? Oh, good question. Glad you asked. This is the part you can write down. I think should write down. If work is the transfer of energy, of kinetic energy is the ability to do work. I'm going to say that again because that sounds so stupid that I'm going to say it again. I mean, it sounds, it's not stupid, and I'm not joking, but it sounds stupid, maybe. Work is the transfer of kinetic energy, or work accomplishes the transfer of energy. Like, that's not what it is, but that's what it does, right? Work transfers kinetic energy. What is kinetic energy? Kinetic energy is the ability to do work. Now, I'll say it one more time. Kinetic energy is the ability to do work. In fact, to be more specific, because it turns out to be more specific, kinetic energy is the ability to do work by virtue of motion. So what we're saying is at the end, the bigger you are and the faster you're moving, the greater an ability you have to interact with something else and change its motion. The faster you're going, the more you can knock into something else and get it to go fast, with the net result that you'll go slower. Okay? It is a circle. It is like circular logic in a way. When you do work, you transfer energy. What is energy? It's your ability to do that. Energy is your ability to transfer energy. If it sounds like a circle to you, then you are hearing me. But like I said, I think right at the end of last class, it's like economic transactions and money. Money is the ability to spend money, right? I mean, why do I want money? So I can buy things, i.e. I want money so I can give it up, comma, yo, right? That sounds utterly stupid unless you take into account the reality that when I give up money, what do I do? Why do I do that? To get something of equal value that is in some form other than cash, right? Like, I give up $100 to get 20 packs of Pokemon cards, TM, rights reserved, not paid advertisement, etc. Right? I pay $100 to get 20 packs. The assumption is that the value is the same, but the form of but I don't want my value in the form of cash right now. I want my value in the form of cards. So I make the trade. Same thing with money. Same thing with energy. energy is the ability to do work. Work is a transfer of energy. But the reason this like gets us anywhere in life is that it turns out energy comes in different forms. So we commit these transactions, we do these transfers so that we can convert ultimately. Either we can bring energy from one place to another, where one place where it's not needed to a place where it is needed, or we can bring it from one form that we don't need to a form that we need, right? But bottom line, work is the transfer, the act. Energy is the commodity, so to speak. The state, the technical term for that in physics is the state function. Okay, that's the background. All right, I'm looking at the time. Okay, so let's talk about this homework assignment. We're not going to get that far in it, but let's start it. We have this boulder at the top of a big inclined plane. The inclined plane is 11 meters high. Like, I don't know offhand how long the plane is, but I know it's 11 meters high. And I know the plane is inclined from the horizontal at 33 degrees, right? In other words, let's be clear. Like, the height of the plane is 11 meters and the angle from horizontal is 33 degrees. So h, lowercase h, means vertical displacement, right? It doesn't mean length in this case. It's not like the h, I'm just being clear. Or that 11, I'm trying to be clear. That 11 meter figure is not, it's not the length of the hypotenuse. It's not the length that the ball is actually traveling. It's just like the height that it drops. And similarly, theta, just to be clear, is the angle of inclination, like we often have with inclined planes, but measured from the horizontal, or the horizon, if you like. Okay. So they ask in part A, what's the work done by gravity on the ball, on the boulder? Well, I'm going to label a coordinate system like I always encourage all of us to do. I'm going to label down as positive and up as negative, because that's the way the ball is going. Or I'm going to label to the right as positive and to the left negative, because again, that's the way, because so that positive matches up with what the ball is doing. But more specifically, I'm probably in a moment going to tilt my head and label down the plane as positive, as we did with the lab, right? But here's the thing. I'm going to get into that in a minute. And you always have to choose your coordinate system and label your axes, right? Always. And like, that's Galileo. But before we go any further, no matter what labels you chose, no matter what direction you, even if you said that down was negative, whatever answer we're going to get for the work done by gravity, whatever answer we get for the work done by gravity, it will be a positive answer. It'll be positive work done. Because whether we call down, if we call down positive, then we're going to do a positive pointing force times a positive pointing displacement. And if we do that down is negative, we're going to get a negative pointing force times a negative pointing displacement. Like, no matter what, if you look in the situation, the boulder is ultimately traveling in the direction that it's being pulled. So the work is successful, right? There is full agreement ultimately between the direction of the force and the direction of the displacement. So that is positive work. Like, whether you're doing positive times a positive equals a positive, or a negative times a negative equals a positive, either way, it's going to be positive, right? Okay. And that should make sense. If we're thinking of work as a transfer of energy, we know this ball is going to speed up as it's going down. So I just want to alert you to like how the signs work. Like, positive work means you give to the boulder kinetic energy. So it's going to speed up. And positive work means that you're pushing or pulling successfully in the direction something's actually going. Okay, for whatever it's worth. So we're going to get a positive answer. Now, how do we do this? We have to be a little careful now. Okay. First of all, let's look at our free body. We're doing force times displacement, so we've got to look at the forces, right? The free body diagram has gravity pulling down, straight down, has a normal force pushing up at an angle. Now, first of all, the question's asking, what work does gravity do? So I only have to worry myself about the force of gravity. Like, the normal force is in the problem. The normal force is a force. It's in my free body diagram. But first of all, the question isn't asking what work the normal force is doing. So I'm not going to put that into my calculation. But second of all, by the way, even if it did ask, if it asked what work is the normal force doing, in fact, it probably should have asked, it'd be a good question. If the problem had asked, what is the work, how many joules of work is the normal force doing on this object? Just to be clear, the answer will be 0, right? Again, that's not in the homework, I'm just saying, like, because, I mean, even though the normal force is a force, and even though there is displacement, remember, work is a dot product, a scalar product of force vector dotted with displacement vector. Strictly speaking, we always do the force magnitude times displacement magnitude times the cosine of the angle between them, i.e., the summary of last week, but we're about to see it now. It's like, i.e., you only multiply the component of force that is parallel to the displacement, so that you could treat the two vectors as though they're just pure numbers on a number line, and therefore get a pure numerical answer. You're only looking at parallelism. Force only affects the displacement along the axis that it's acting. So, long way of saying, just if you're like, the normal force is fully perpendicular to the motion, to the displacement. So just as a baseline for this analysis, the normal force is doing no work. We're being asked to analyze the gravity, however, and the gravity most certainly is doing work. So I'm going to break up the gravity into two components, like we did in the lab, like you did in the lab. Like, I'm tilting my head. I'm saying, since the thing is going to accelerate along the plane, since it's going to be displaced, the boulder is going to be displaced along the plane, I'll tilt my head, I'll call that the x-axis, I'll break up gravity. So I'm saying this is like approach number 1. I think the standard approach, the right approach, the best approach. I tilt my coordinate system, I break up gravity into two components, right? Now, mg cosine theta is just fighting against the normal force. Mg cosine theta is perpendicular to the motion, just like the normal force is. So mg cosine theta is not doing any work. It's entirely mg sine theta that I want to analyze. That mg sine theta is pushing along the axis of motion. So I'm going to do mg sine theta times the length of that hypotenuse. But one thing to be clear, and so I'm focusing on the whole angle aspect here and the whole dot product to give us practice with the dot product. But you might ask, wait, what happened to all this calculus? Like, isn't there an integral? Like, I hate the integral. Don't we have to deal with the integral? Ultimately, we really do have to deal with that integral. But the integral is there. The integral sign and the integral operation is there to account for the possibility. Remember, we said last week, the integral is part of the definition in order to account for the possibility that force varies as a continuous function of the position of space. But here, F is not varying. In this case, whatever complicated angle is going on, whatever complicated coordinate systems are going on, gravity is gravity. It's not changing from place to place. It's a constant force. So in this case, it can come out of the integral, so to speak, right? And I think many of you, even if you're still sort of uncomfortable with how to set up integrals or why, oh, here comes our interruption. Oh, and one of our lights in the class. Anyway, here comes our interruption in a minute. But even no matter what level of comfort you're at with setting up integrals or the meaning of integrals or what, I think many of you know operationally that when you have an integral, if the dependent variable in the integral is a constant, if it doesn't depend, like in this case, if f doesn't depend on x, f comes out of the integral. Why is that? Well, I mean, it does. First of all, it does, and it will here. The f will come out of the integral. So we just have f times integral of dx. And integral of dx is just x, right? The sum of all the little infinitesimal sections of the total displacement. If you, like, integral just means add up, right? So the integral of dx literally means add up all the little subdivisions of x all together. When you do that, what you get is the full x. Like, it's not just a memorizer. It really makes sense if you think of an integral as a sum. And if the integral of f dx really means f1 times dx plus f2 times dx plus f3 times dx plus f4 times dx, which is what it means, right? That's all an integral really means. It means add up this whole continuous collection of products. That integral of f dx really means f1 dx plus f2 dx plus f3 dx plus f. Well, if all the f's are different, you really have to do the calculus. But if all the f's are the same, if f1 equals f2 equals f3 equals f4, then you're really just saying f dx plus f dx plus f dx plus f dx. So you factor out the f and you just have f times this long sum of dx's. Like that, for anybody who caught that, I'm just trying to explain why we always say you can take the constant out of an integral. You're just distributing that number across a long, you're just distributing it across multiplication. Across addition. That's all you're doing. So anyway, that's what's happening here. The force is constant. It's not changing in this problem, so we can take it out of the integral and we don't actually have to do any calculus. By the way, that will continue to be true for the rest of this particular homework assignment because it's called work done by a constant force. So even though I'm totally trying to drum in that you understand the calculus and why the integral is being set up and why this thing is defined as an integral, you don't, oh, here we go. You don't actually have to get into the nuances of the integral for this homework assignment. Okay, hello, welcome, ladies.
Your homework assignment is to make him stop talking.
Right. Yeah, good luck to everybody. Okay, but I will I am stopping them 15 minutes early, so I'm gonna keep. Okay, love you. Okay, oh, here we go. Okay, but they can't see. Oh yeah, they can't see. Okay, well, okay. They can't.
Which is better, the mud chip that I'm holding?
They can't see it though.
Can't hold up.
Okay, yeah, stand back a little bit. Okay,
Which is better, the mud chip or him?
Clearly the mud kip, we all know this. Okay, I have to go back. They're ending early, so I have to go back. But lovely to see you.
Mud chip or him?
Felix.
Huh?
Hi, Felix.
Hi.
Okay, all right, very nice. Yes, clearly Mudkip is better than me, and clearly Empoleon is the evolution of.
Okay, I want you all to raise your hands if you
No,
think he's
Felix,
better than Mudkip.
No, we know I'm not. But they've got to learn, or I've got to try to teach at least. And you got to go upstairs, and I will be with you shortly.
They don't have to learn and you don't have to teach.
They don't have to learn, but I do have to teach.
What, you need money or something?
Something like that. Yes, I need to keep.
Boo.
Okay, I love you. Where do the packs come from?
Yo, I'm stalling you.
No, stop. No, okay, enough. Thank you. Love you. Okay, all right. All right. I mean, okay. Yeah, you're welcome. All right. Okay, I will see you soon. Okay. All right. So I'm just flip the page. So all of that, I'm glad we're laughing. Oh, yes, we're all okay. He's on roll. Yes, exposed. Oh my God. Yeah. All right. Right. And they wrote LMAO in the chat. You can go look that up now.
Lame-o.
He said lame-o. All right, that's true too. No, go. In this context, sure. Okay, I've got it. Thank you. Love
What
you.
does it stand for?
Laugh my something off. I can't remember the third word. You'll look it up. Okay. Okay. Laugh my butt off. All right, close enough. Thank you. Yes. Okay. Okay. All right. So everything I just said, I'm looking at the time, I promise. Okay. Everything I just said, not about him, but about physics, was all the way of justifying that. I'm going to skip the calculus part now. It's not a way, like, we need to know it for the general definition. It will come up whenever we have forces that vary, but this force is not varying. So I'm taking the force out of the integral. So I get f of integral dx. Integral of dx is just x, therefore top line of this sheet. Like, and I hope you understand that. Like, we're now saying in this context, like, notice it's not a triple equal sign, but in this context, when f is a constant, f equals f vector dot x vector. Now I'm reminding you. So now the real issue that we have to get into, like the thing that this problem is really trying to get us to see, is how this whole dot product and the angles and everything work. So remember, f vector dot x vector means, I think what I was saying a minute ago, it means the magnitude of f times the magnitude of x times the cosine of the angle between them. Cosine, because cosine measures parallelism. right? This is a short, like sometimes you literally write out each number and then you literally look at the angle between them and you literally take the cosine and you multiply it all together. But sometimes there's other ways of seeing the same result. The thing that this means, when I write when I write fx, in fact, let me be really specific. When I write like fx cosine theta, what I'm really saying, and like I said last week, I'm saying the component of force that is parallel to displacement times the displacement. That's what I'm saying. That you, however you do it, that you just find the two components that are parallel to each other and multiply them, but you don't multiply in any other components, right? So in this case, what I'm saying, right, so where theta means the angle between f and x. Okay, so here in this case, as it says at the bottom, F, so here in this case, we've sort of done that. When we resolved the mg components and we said, okay, the component of mg that's going along the plane is mg sine theta. Okay, we've in effect done our cosine operation already. We've gotten the component of mg that is lying along the plane. Before I go any further, you might say, it would be, okay, I'm going to pause here because this is a little tricky. I'm going to say it. I didn't exactly write it down, but please bear with me. If you're following all this, it would be very reasonable to be thinking in your mind, like, okay, but why is it sine rather than cosine? I thought he's saying cosine. Cosine, yes. I'm saying that the definition of the dot product, the definition of the dot product is that you multiply two components together that are parallel. The way to multiply two components that are parallel is to multiply their magnitudes and multiply by the cosine of the angle between the two components. But the theta that's given in this problem, see, this is just kind of like that whole lab issue. Look at the picture of this problem. The theta that was given there, the theta that was given is not the angle between mg, is not the angle between mg force and hypotenuse displacement. That angle that's given is measuring the incline of the plane from the horizontal. But gravity is vertical, right? So I'm not trying to be annoying. I'm not trying to be annoying. But I'm saying, like, the standard way to talk about an inclined plane is to measure its angle from the horizontal. Okay, we do a billion things with that fact. But now we're getting into work. Work is about multiplying the components of force and displacement that are parallel with each other. Well, the force here is vertical and the displacement is on an angle. So the angle between those two vectors, okay, the angle between those vectors is not 33 degrees. It's the complement of 33 degrees. It's 57 degrees, right? So the sun, so what I'm really trying to say is yes, we still do want the cosine of the angle between them, but the cosine of the angle between them is really the same thing as the sine of that. We want the cosine of that upper angle. That's the same thing as the sine of the lower angle. I could maybe put it other ways, let that sink in, but I'm assuring you that I'm not contradicting. I'm really saying, how about we do this? I could do something like this, if this helps at all. I'm going to keep going and say, I mean, if you're sort of with me, but not entirely, you can certainly put a question in the chat. But I'm saying so I'm saying the cosine theta rule is you do whatever you need to do to get the components that are parallel. In this case, I know that the component of gravity that is parallel to the plane is what we already defined to be mg sine of that angle at the bottom of the plane. It would be the cosine of the upper angle if we wanted to talk about the upper angle. I don't know if that helps or not. Anyway, so the force is mg sine theta. There's nothing in the chat that's possibly good, possibly scary. But so the force is mg sine theta, like we said in the lab. Now we're going to multiply that by the x along the plane, right? I mean, and then we'll have the work done, and then I'll be able to finally stop talking and make everybody happy. But what is the x along the plane? It is not 11 meters, right? Let's be clear about this. I think this is a more straightforward point. The displacement along the plane is just that, literally the displacement along the plane. 11 meters, that given number was the height of the plane. So if we want x, if we want that hypotenuse, we need to do SOHCAHTOA or something. We need to realize that the sine of the angle down there at the bottom is h over x, is opposite over hypotenuse, right? So the hypotenuse, and this is all the letters are kind of confusing because I'm using h to mean height, not hypotenuse, and I'm using x to mean hypotenuse. That's all. You just got to, I mean, this is where you just got to keep track of it and stay with me. I mean, I promise you this, we're not doing that in order to be confusing. We're just doing it because there are a lot of details to manage. So I'm saying x, the displacement is h over sine theta. Therefore, x equals h over sine theta. So finally, the work that's being done here by gravity on the boulder, the work that's being done is, if you think about it, mg sine theta times h over sine theta. Like, well, right? I'll say it again, right? The force is mg sine theta. The displacement is h over sine theta. So the sine thetas cancel, and we just get mgh. Like, all of my talking, all of this sort of keeping track of all these details actually led to a very simple result, which maybe you got some other way, or we'll see in a minute. But I am now, and the key, so I'm saying the work done by gravity is the force times the displacement. Now you look, well, right, but that means at the end of the day, in our attempt to take the angles very, very seriously, at the end of the day, we didn't have to worry about the angles in a way, it looks like. But why? Okay. Okay, so I'll get the answer too, sorry. So the answer, the numerical answer for this, I'm saying the work done by gravity is the mass times the acceleration due to gravity times the 11 meters that was given in the problem. So you get 850 times 11, like positive 9.35 times 10 to the third joules of work. Okay, so it is positive, and it's a huge number. And let me pause for a second. It is possible, of course, that you might have just taken the three numbers that were given in the problem, or, you know, the two numbers and gravity. You might have just like multiplied them together and gotten this answer right without really talking about it as much as I just did or thinking about it. But be careful, what I don't want you to think is that in general, you can't just take any force that you're given and just multiply it by any, you can't just take any number of newtons that you're ever given and multiply it by any number of meters and assume that that correctly is the work being done. I mean, for example, if we had multiplied the normal force by the 11 meters, that would not be the work being done. But the reason here that we ended up getting such a simple answer after all of my discussion about cosine is that we could have taken approach number 2. And this might be more similar to the approach that you might have taken, but I don't know if it was conscious or not on your part, if you did. Like everything I just said, let's think about this for a minute. Everything I just said was an attempt to take the component of force, let me back up for a second. The force is purely vertical. The force is gravity, mg, straight down. The displacement is along this slant, right? That's the issue, is that we have a force and a displacement that are not lined up. So we have to do something with angles in order to take that into account. Like what we really are saying is not all of gravity is being devoted to doing work on this boulder. I mean, we really are saying that only a portion of the boulder's weight is in fact doing work on the boulder and succeeding in sending along the plane. The other portion of the boulder's weight is just keeping it stuck to the plane. But that's the mg cosine portion, right? Like literally we're saying that only the mg sine theta portion, only that fraction of the boulder's weight is contributing to work, which is to say only the mg sine theta component of the weight is transferring energy to the boulder. Only mg sine theta is making that boulder speed up. So we really did, okay, again, because gravity is pulling straight down, but the boulder is not going straight down, it's going on a slant. So we actually have to take into account that fact and say, okay, angles are somewhat involved, like dot products are involved, blah, blah, blah. So what we did in the analysis that we just did is we took the component of force that was parallel to displacement and we multiplied it by displacement. We took this component of force and we multiplied it by this displacement. That was the correct thing to do. And we found, oh, that sine thetas beautifully canceled out. After all of that thought, we ended up with this like seemingly simple thing of MGH. The reason we got a simple thing is we might have looked at it the other way. We might have said, oh, instead of component of force that's parallel to displacement times displacement, we could have said force times component of displacement that's parallel to force. What the heck do I mean? In other words, gravity is pulling straight down the whole time. So if instead of multiplying mg times h over sine theta, if we just multiply mg by h, then we're multiplying two components that are parallel with each other. In other words, what all the, and again, you might have not done this problem at all, or you might have done this problem in 2 seconds, like much faster than all my talk, but you might not have known why. What I'm trying to say at the end of the day is multiplying this component of force times this full displacement gets the same result as multiplying this component of displacement by this full force. And the latter, of course, is easier in this. I mean, multiplication is commutative. You could do it either way. But but in the end of the day, going, oh, gravity is only pulling straight down. So the only aspect of our displacement, the only portion of our journey that matters is the straight down portion, because we only care when we're calculating work, we're only multiplying parallel components. So it's true that if we stood back and look at this, we could say, oh, gravity is mg, the height is h, the work done by gravity is just force of gravity times h. And so from now on, that is what we're going to say. So that's what this page says. Whether we multiply the displacement by a component of force parallel with displacement, or we multiply force by a component of displacement parallel to force, whichever way we do it, we end up saying that the work done by gravity to move an object from a certain height to another height will always, from now on, like this is now a truism, this is a takeaway. This is the purpose of the problem. Even though I know we're not getting far in the numbers yet, the purpose of the problem, or a purpose of the problem so far, is to say from now on, if you could take to the bank for Felix, you can memorize that work done by gravity, not all work done by everything, but the work done by the force of gravity will always be mg times h, where h is the vertical displacement that an object undergoes. In other words, I don't care. You can go down a spiral staircase. You go on a curly Q water slide. You can walk as far a journey as you want with all kinds of curves and horizontal displacements, and none of them matter to the work that gravity is doing, because gravity is always just pulling straight down. So from now on, the work done by gravity is always mgh, where h, it doesn't mean displacement, it means height. It means like specifically only the vertical displacement from one point to another. Okay, that's the takeaway of that. Okay, I know it's a lot, but that's an important takeaway. All right, this page, you'll get the PDF, but this page literally just says everything I just said, I promise. Don't worry about it. And then this page says what I just said. No, from now, this is the takeaway. From now on, work done by gravity depends only on vertical displacement. From now on, the work done by gravity, this is just gravity that I'm talking about. Oh, hello. The work done by gravity is mgh. Oh, yes, sorry, Melita, yes.
We're saying this applies to just this problem or all problems?
Oh, wait, great question. This is such a big deal that it applies to all. I'm so glad she asked that. This applies to all problems in the future, and it applies to physics 204, as long as, yes, this is a general result that you can like memorize and rely on, as long as what we mean by that is that from now on, always the work done by gravity in all problems equals mgh. But like, so yes, like the answer to Melita's question is like, this is a big a big like universal thing that you could take away, but it's universal about gravity. Like I'm not saying, well, you'll see. Okay, I hope that's clear. You're gonna see. I'm gonna do like one more quick question. I'm watching the time. We have like 4 more minutes. Okay, till Chris's our strange 15 thing. But if you go to the very next question, and that's as far as we'll go today. If you go to the next question in the sheet where it asks the work done by friction, okay, now it's asking friction. So this is again to sort of answer Melita's question. Like now we're talking about friction, not gravity. We're not saying gravity's not there, right? But now we're just specifically asking what's the work done by friction now. So friction is it totally pointing along the plane. Like if I do the free body diagram, this is a free body diagram, right? Even gravity, when I broke up into 2 components, even when I tilt my head so that, my x-axis is the plane and my y-axis is like, so if this is my x-axis, hello, and this is my y-axis. So gravity had to be broken up into cosine and sine in order to accommodate that. But friction is just literally there. Friction is along the plane already because it comes from the rubbing of the object against the plane. So like wherever the object's going, that's where the friction is, right? Friction is different from gravity. And friction's always against the motion. So when we're doing the math, like strictly speaking, the angle between the friction and the displacement is 180 degrees, 180. Like in other words, the displacement is directly along the plane and friction is exactly the opposite of that. So the cosine is -1 in the case of friction. And so you literally just multiply the force of friction, which the problem gave us 70 newtons, times the x. Now the x is still h over sine of 33 degrees, right? Like the h is bigger than 11. It's whatever, I forget what but it's bigger than the h is. Right, the h is like 20.2. Not the h, the x is like 20.2. But you just literally multiply that x by the force of friction because they are already parallel. And then you multiply by negative. I'm saying the same thing over and over again. So you get in the end that the work done by friction is negative 1.41, approximately negative 1.41 times 10 to the 3rd joules. Long or short story long, I'm saying we're doing the same definition of work as before, but here you don't get a canceling out kind of thing. Here, so to specifically answer Melita's question, and then I'm like done talking for today. I'm saying the MGH memorizer, yes, it's true for all problems, but what is true about it is that the work by gravity in all problems is MGH. This question here is the work done by friction, so that's not MGH. Does that make sense, Melita? Or okay. Oh, Melita. Oh,
The
hey.
negative comes from the -1 that we're multiplying from the cosine 180, or it comes, yeah. Okay.
Yeah, totally right, and that yes, and it's 180 because I just know that the nature of friction is if you're going to the north, friction is pushing you to the south. So like it's 180 because of this picture here, like gravity's pulling you down, but friction's pushing against you. So they're literally opposite each other. Like yeah, I don't know how to say it better, and I don't know if this helps or not, but yeah. So I'm in the end of the day, and I'm saying that will always be true of friction. If you're looking for general like takeaways or memorizers, the work done by friction is always negative because it's always, the force is always opposite to the displacement when it comes to friction. And that's why friction's therefore always taking energy away. If friction's left to its own devices, it's going to slow you down. Now, again, I mean, there could be other forces too, so the network might not be, negative, but friction takes kinetic energy away. It's negative work.
That makes sense.
Oh, okay, cool, great. Thank you for saying that. And to everybody, since that was such a good question, I swear this is I'm putting down the cannoli and leaving the gun or whatever. If you think so, if we're trying to figure like what of this is takeawayable to other problems and what isn't, I am saying the work done by gravity is always mgh. I am saying the work done by friction is always negative. But what am I saying about positives and negatives when it comes to gravity? When it comes to gravity, like if you are falling down, then the work done by gravity is indeed positive mgh. Like if you're falling down, if you're going down, then you're going in the same direction that gravity's pulling. So it's in agreement. The cosine's 0, not 180. It's positive, and you speed up. But if you're going up, like when I throw something up, when something's going up, gravity's pulling down on it still. So when something's going up, then the work that, like up to a height h, then the work that gravity's doing on it is negative mgh. And that's why the thing will be slowing down while it goes up. I don't know if that's too much or too little information, but that's, oh, sorry. Oh, right. If integral, oh, good, Chris. I think it's it. Yeah, exactly. If the exactly what Chris says in the chat. If the force and the displacement, it's not even a joke. If the force and the displacement are in agreement, it's a truism that the work is positive, like absolutely, whether it's a positive times a positive or a negative times a negative. If the force and the displacement are in agreement, then the work is positive. That means the force is accomplishing what it's attempting to accomplish. So that means it's positive work, and kinetic energy of the object increases. But conversely, right, if you're pushing against the displacement, that means you're doing negative work. That means it'll slow down. Absolutely. Okay, it's 4:07. So I'm going to say this because I promised it's right in between 10 minutes and 15. I'm going to say, good. Well, oh, good. Okay. So I'm going to say, if you've done the course evaluations, thank you very much and goodbye. And I'll see you in 2 days. And there's no new homework. And if you've done your homework, there's no new homework. If there's any homework you haven't done, you could still catch up on it. There's still time. If you haven't done the course evaluation, please hang out and use this time right now to do it now, please. Or if you need help with the link, whatever. I'm not looking at you doing it, but just whatever. So I'm going to stop the recording. I'm going to stop the recording.